Welcome everyone to Lab 4. We're going to talk about asymptotics and scaling and behavior of sequences in the limit. There's some important concepts here that we'll need for inference down the road. It's a little bit more of a technical topic, but one that will be important in general for handling what we need to handle later on. So let's get started. So I'm going to start in general by talking about properties of sequences. So I need a sequence. So I'm going to let xn be my sequence. And the way I think about this is I have a random variable x1, random variable x2, random variable x3, dot, 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 and they're converging to something. And they're converging to a point. And I'm just going to let that point be x, no subscript. Makes it a little bit easier to think about what's going on, I think. The x1, x2, x3 might be sample means that are getting more precise as you get more data. They could be maximum likelihood estimators. They could be different things. And x could be a parameter, mu, an expected value, theta. But I'm trying to leave it a little general. And one important piece that you remember from probability class is that we need the first absolute moment to exist. All right? And so then we can talk about convergence properties, namely that if the expected value of the absolute value of the limit exists, then what that tells us is that there is a limiting distribution, right? So the limit of a particular distribution is going to be this f of t, okay? And that'll be the limiting distribution of whatever, x, whatever we're looking at. I think it'll become pretty clear as we go through what's going on. So there's two key sequences, two key concepts for sequences, and they both have to deal with the limit, and that's whether the limit goes inside or outside the expectation. And this is important because the limit is a function, and we know from Jensen's inequality that the expected value of a function is not equal to the function of the expected value. So the expected value of the limit, for example, okay, is not necessarily equal to the limit of the expected value. All right? And of course here, this whole piece in here, this limit of xn, this is just the expected value of x. Right? Oh, here it is right up here. All right? The problem is you can't pull the limit through the expected value, or I say you can't always pull it through. You would like these things to be equal in the long run, because then you're going to have nice behavior of moments, and you're going to have, I should say, congruent behavior of moments and distributions. And so we'll see some examples as we go through. Okay? So the limiting and asymptotic expectation do not have to be equal. So this is the limiting expectation. You're taking the limit of the expectation. The asymptotic expectation is what is the expectation of this particular thing at the end of the limit of the sequence, right? Which can be random. So let's go through, and I think it's just helpful to just jump in and take a look at some examples. So let's take a very simple example. x1, x2, x3, xn, they're independent, identically distributed from a normal distribution with mean mu and variance sigma squared. And for some constant c, okay, for some constant c, I'm going to define a special random variable. And that, let's see, where can I write? So I'll just write it up here. So this special random variable, let's use purple, because purple sounds like it's kind of a purple day. I'm going to take the sample mean and I'm going to add a little bit to it. And I'm just doing this to show you, to illustrate all the properties. But what will happen is we will see maximum likelihood estimators that are biased, and we'll break the maximum likelihood estimator up into parts that may basically you want to know what the bias is, and you want to see how it behaves. And so that's kind of what we're doing. We're taking something that's unbiased estimate of mu and we're adding a little bias here. And that's a new estimator, so I'm going to call that Tn because I need to call it something, and Tn just sounds good. Again, the n lets me know that there's something going on with the sample size. So here, the bias, right? The bias is C over n because the expected value of Tn is equal to the expected value of x bar n plus C over n, because that's a constant, so it's mu plus C over n. So the bias is C over n. Now, what happens at the limit? Well, you can compute the limiting bias, and that's this thing here. And so all you end up doing is you take the limit as n goes to infinity of the expected value of the bias, C over n. And there's nothing random here, so it's just the limit of C over n, which is 0. All right? So there is no limiting bias. At the limit, Tn will end up at mu. And so just before we talk about the asymptotic bias, this is an important point. Tn is going to mu. But so is x bar. That's going to mu too. They're both estimators of mu, right? Why might we prefer one over the other? They're converging to the same thing. Well, the variance of one might be bigger than the variance of the other, for example. Now, I wonder if that's the case here. I mean, so I'm going off script now, but if I take the variance of x bar, let me actually write that so somebody can read it. If I take the variance of x bar n, that's going to be sigma squared over n. If I take the variance of Tn, that's also sigma squared over n. Well, okay, so wait a second. They end up at the same place. They have the same variance. What's different between them? Well, Tn has a little bias. So Tn's mean square error, the mean square error for Tn, let's see how to write. So the mean square error for Tn is going to be bigger than the mean square error for xn, because this is going to be sigma squared over n plus the bias squared, c squared over n squared, is going to be bigger than sigma squared over n. Right? Okay, so different estimators, but we're changing the properties of one. And now we begin to see why it's important to pay attention and keep track of, well, bias and variance and mean square error and consistency, because estimators can be similar on some of these criteria and different on others. Now, let's take a look at the asymptotic bias here. The asymptotic bias, hello. Let's scoot this up here. I want to just have some room to write. So the asymptotic bias is 0. Well, what is the asymptotic bias? Well, the asymptotic bias is the expected value, as I've kind of written it, of this thing above. Right? So if we actually go back and take a look at this thing, that's what I've written. And now, very often, this is a harder quantity to deal with. Because the limit of xn is just x. So this looks like, just the expected value of x. Right? But what we do usually to analyze this is we usually center and scale x. When we talk about asymptotic bias, we almost always center and scale it. And that's what I've done here. So I've taken Tn and I've centered it and scaled it by root n. And we'll talk about why this is helpful to do in a second. I think it'll become obvious, but I'll talk about why. So I called it Tn star. Okay? So if I take Tn, which is this thing here, and I subtract mu, and multiply by root n, I get x bar minus mu, and then I have this plus c over root n, right, times root n, because there's a root n here. This root n canceled with that root n, right? So I get c over root n. So now what happens? What happens to this? Well, this looks to me like this by the central limit theorem is going to converge to a normal 0, 1, right? And actually, it's actually z sigma, because I'm not dividing by sigma on the bottom. So it converges to a normal 0 sigma squared. And then c over the square root of n is going to go to 0. And it's going to go to 0 at about the same rate that this thing converges, that this first thing here, this thing here, converges to a normal distribution. And so it doesn't provide any interference, so this goes to 0, and I end up here with a normal distribution 0 sigma squared. So my scaled sequence here is normal 0 squared, and then to compute the asymptotic bias, what we do is we just take the expected value of the limiting piece of this. And the important thing about the asymptotic bias is that almost all the time you're really looking at the bias in a standardized and scaled variable. You're looking, you want to standardize, you want to scale this thing, because you're looking at the distributional properties of this thing in the limit, okay? So let's take another example. I'm going to do the same thing, and all I'm going to do is I'm going to change Tn here ever so slightly. So let's scoot this up now. Okay, so here's the same example, except I'm going to divide by c over root n. So before I had c over n here, right? So now I'm going to make the bias go to 0 slightly slower. So this bias is going to stay around for a little bit longer than it did in number 1. Because number 1 I'm dividing by n, and now I'm dividing by square root of n. All right, so let's scoot this up. So now, same sort of calculations. This implies that the bias is c over square root n. The limiting bias is still 0, right? Because the limit, as n goes to infinity, of the expected value of c over root n is 0. Okay, no problem. What about the asymptotic bias? Well, what do I do with the asymptotic bias? Well, I have to standardize and scale that guy. Okay, whoops, standardize and scale is maybe bad, so maybe it's better just to say center and scale, okay? And just to make it clear, I think I said standardize and scale, which is kind of the same thing. Center and scale is what I have in mind. All right, so I took Wn, I centered it by the thing I want to estimate, and I scaled it by multiplying by root n. So now what happens is I still get x bar minus mu. I still get x bar minus mu times root n. That all comes from this first piece here. All right, and mu, actually. And, but now I have a c times root over n times root n, right? Because in this w here, this guy is in here. The root n's cancel and I get c. And this converges to normal 0 sigma squared plus c, and so that goes in law to normal c sigma squared. So now there's some bias. This limiting distribution is off-center. It's not 0. The asymptotic bias here is c. And the reason this is important is because what we're basically explaining is how bias sticks around. And in this particular case, you can see because the bias is only divided by root n, and if you look at the distribution of xn, if you look at the distribution of your estimator, the bias does not go to 0 fast enough to avoid being a problem. In fact, it's too slow. It's actually just at the rate that xn is converging to a normal distribution. And so it sticks around. And so you can see this bias sticks around. All right? So what that means is whenever you're doing some limit, what you're ending up with is you're off by c. And I'll draw a picture of this in one particular second. But I want to make a point that things are still consistent and the bias still goes to 0. What you're throwing off is the distributional properties of your estimator. Okay? So, although Wn has non-zero asymptotic bias, it's still consistent for mu. In fact, it's consistent in a very strong way. It's consistent in mean square error because the mean square error goes to 0. So the variance plus the bias squared goes to 0. So Wn, okay? So the way I think about this is, yeah, let's draw a picture. I think that would be easier. So let's see if I have a little space right here, and we can try and draw a picture of what happens. We do. Here's a little space. All right. So the way to think about this is this. You have, imagine you are looking at a particular sequence. And I'm going to draw a graph here. Okay? And this is n. This is as your sample size grows. And what you're saying is that at any particular sample size, there's a normal distribution normally. So let's draw a normal. So we might draw a normal distribution. And then as n gets bigger, you might draw another normal distribution. And as n gets bigger, another normal distribution. And normal. And these are supposed to be centered right around 0 here. Right? And so what this picture describes is the paths that you might see, right, for the sample mean. There you go. There's even some sound effects, okay? And that's what we think about when we think about the behavior of the sample mean. It converges to mu. This is mu, right? X bar n converges to mu. And its distribution, root n, x bar minus mu, converges to normal 0 sigma squared. And that should be okay. You know, I get that. That's what we're used to. Now what happens if I add some bias to xn? Well, let's go back to the first thing. If I add bias c over n, so if I add this bias, c over n, what happens is that this picture here changes a little bit. Okay? But not, it changes a little bit, and in a way that I'm going to show you here. So now here's n, and let's say c is positive. So you might end up with a little bias here. You might end up with a little bias here. You might end up with a little bias here. But what happens is eventually these sequence of normal distributions end up right on track. And they don't shrink yet because n is not large enough for them to shrink. So you have some sequences that have some bias, but that bias is going to 0 faster than the set of sample means are converging to a normal distribution. And so eventually you end up right back to the same behavior that you might see here. Okay? Because the bias, c over n, is going to 0 fast. Right? The behavior of convergence to a distribution here, this is going at a root n rate. That's this at the root n rate. That's the rate right out in front. Okay? And this is going to 0. This is going to 0 at an n rate, so it disappears quickly. Now let's take this other case. Let's take this other case here, where we've got c over root n, because that bias is not going away fast enough. What sort of picture would you get for this? Well, let's draw a picture and let's see. So here you go. Here's your picture. Here's your sample size. And what happens here is that you get some normal behavior and you do get some condensing, except the bias is going away slowly. Slowly. Okay? I don't even know what those are that I'm drawing there. That's just some ugly stuff. these things are going to 0 slowly. And in fact, I'm going to get rid of some of these and just make it look a little faster, because I think everyone's got the idea now. But they're going to 0 slowly. These are normal distributions, and they're never going to quite get centered on mu. In fact, for any distribution that you look at, if you take, let's see, so this was x bar by itself. This is x bar n plus c over n, and this is x bar n plus c over root n. So this was Tn, and this was Wn. And then what happens is here is for any point that you take anywhere in the sequence out to infinity here, and you look at the normal distribution, that distribution, if you scale it, so if you do root n Wn minus mu, that thing is converting to a normal distribution c sigma over n. So that means you're always going to be off by c. By c, effectively, it'll turn out to be c standard errors, which I'm going to talk about in a second. That's the scale. But you're always off by c, right? And you can kind of see here that you're off by c, essentially standard errors. There's no sigma there, but it's over root n. All right, and so this is when, the way I kind of think about this is how you would describe having some positive bias in an estimator that's going to 0. The bias is always positive, but it's shrinking, but it doesn't go away fast enough so that even in the limit, even as the sample size gets bigger, you can't get rid of it. And part of the reason that you can't get rid of it, one way to think about it is, let's see, the width. Oh, that's disgusting. Let's see if I can make this short. The width of this thing, the width is getting smaller, right? In some sense, normal distributions go from minus to plus infinity, but the mass of the underneath, say, the middle 99%, the width is getting smaller and smaller and smaller as n goes to infinity, while the bias is maintaining itself. And so the bias turns out to keep that distribution away. That distribution is shrinking in width as fast as the bias is shrinking. And so you're always off by this amount, which is basically c over root n standard errors. So wherever you happen to look, your distribution is going to be off center. And so this is a problem for estimators of the mean that have bias. Even if the bias goes to 0, when you want to use a normal approximation or something, you're going to be off center, and then you don't get good coverage. In the case number 2 up here, your bias is going away faster than your convergence to a normal distribution, faster than your sampling distribution can come together. And because of that, you can essentially ignore the bias in large sample sizes, because first the bias vanishes, you end up on track here, and then you have some convergence to a sampling distribution. Here, as the sampling distribution is coming together in this third example, it's not coming together any faster than the bias is going away, and so you always end up approaching the mean from above. And so the type of bias you have is important. Let's talk a little bit about the scaling of this. This is an important concept, and it's worth discussing. Scaling is important, and I think I can hopefully make this a little bit more real, make a little bit more sense about why it's important, because we're going to use it all the time. And you're already using it all the time. You're already thinking about it. So let's assume I have an estimator of some parameter. Then, of course, as n grows, I'll have a sequence of these things, and they'll approach theta. Now, I'm assuming I know what the truth is. So I'm going to rewrite the sequence by centering it. So I'm going to have a new sequence, which is the difference, how far the estimate is from the truth at every observation. And since theta hat n is consistent, right? So theta hat n is converging to theta, this difference will go to 0. And so this is a sequence of estimators that approaches 0. Now, in practice, you can't construct such thing because you don't know what theta was. And if you did, you'd be out of a job anyhow because you wouldn't need to estimate it. But the idea here is to understand what the behavior is. So I have a sequence of things that are converging to 0. All right. Now, if I want to examine these things, the differences, it can get hard because they're getting smaller. So I can eyeball the differences, till I get to about 100. Then they're going to get really small, right? They may be like in the 4th decimal point. And maybe I can do that on a computer, right? And I can keep looking at the sequences. And then they're going to be in the 8th decimal point. Then they're going to be in the 16th decimal point, right? And so if I really want to see what those differences are, I have to keep multiplying that number by tens to pull it up to see what it is. And just remember, okay, it's in the decimal point. So another way to do that is to artificially increase these differences naturally or to magnify them. This is effectively a mathematical magnifying glass, which is you take your sequence of differences and you multiply it by the square root of n. You blow it up. And when that happens and you're still consistent for 0, we say that you're root n consistent from 0. So the terminology is that theta hat n, right here, is root n consistent for theta if the square root of n times their difference, okay, converges to some distribution. And the distribution just can be anything. The sampling distribution can be anything. It can be chi-square, it can be normal, it can be gamma, whatever it is. It's just got to not be degenerate. Because if it's degenerate, then you have convergence and probability, right? So convergence in law to a degenerate distribution is the same thing as convergence and probability. All right, so let's go back to our example and let's see what's going on. So I have a bunch of x's. They're independent and identically distributed. Normal, mean, mu, variance, sigma squared. All right? And here, I'm going to say x bar converges to mu in probability. Well, what does that imply? Well, I can subtract mu from both sides. It means the differences converge to 0 in probability. All right? But of course, we know that if I take the square root of this thing, if I take the square root of n, x bar n minus mu, that is just ugly. So let's rewrite it. If I take the square root of n, x bar n minus mu, of course that's going to converge by the central limit theorem to that guy. And so that's what this says right here. So the asymptotic distribution is normal, and the asymptotic bias, of course, is 0 because the mean of the limiting distribution is 0. And so here we say that xn is root n consistent for mu, which I think I already said. So let's take a look at what this behavior implies. So why is this useful? And so this is going to be useful because it's going to help us understand the difference between clinical and statistical significance. And here's how that works. Same model as above. Think about the data on the actual scale that you collected. I call this the data scale. So it's the data on the original scale. I haven't subtracted anything. I'm going to look at the sample mean minus its mean. I'm still pretending I have that. And so x bar n converging to mu in probability, I'm just going to apply the definition. That means there's the limit. And there's a limit on the probability that x bar can be far from mu. That's exactly what this is. All right, and I can rewrite this now, okay, as x bar n minus mu converges in probability to 0. And so that is this statement. And so all I've done for that statement is I've multiplied by that. Multiplied by constant from both sides so that you can see what's going on. I'm going to get rid of that because I think it's harder to look at. But now that you can see what's going on, you can say, okay, well, the limit of the probability of this thing being less than this constant. Well, this is a standard normal distribution. So this is the limit of 1 minus twice, because this is the absolute value of being in the tails, which is this. And that goes to 1, because the limit of this thing, the limit of 1 is 1, and the limit of minus 2 phi of this thing is going to be 0, because root n gets really big, and this is the lower left tail. And the area to the left of the lower left tail as it gets really big is 0, right? Because that's basically this thing right here. Epsilon root n over sigma minus 0. And this thing is going this way, and you want all the area to the left. That's what that is. So that's how you get 1. The thing to remember here is that the definition of epsilon is it's on the data scale. So if you're measuring blood pressure, then this is millimeters per mercury. If you're measuring how much money you would pay for something, then that's dollars and cents. If you're measuring heart rate, then epsilon is heart rate. And so this is an important statement, because by saying x bar converges to mu, what you're saying is that the sample mean, x bar, can be arbitrarily close to mu. All you got to do is you wait long enough, right? You wait long enough, and eventually x bar will be arbitrarily close. It'll be within epsilon units of mu. You may have to wait a long time, but you can get there. So for small epsilon, you wait a long time. For large epsilon, you don't wait a long time. All right, now suppose that I take this sequence and I'm going to magnify that. And so I take this sequence and I'm multiplying by root n. Well, now the sequence of differences doesn't shrink anymore. So I don't get my convergence and probability behavior, because the differences were converging to 0. But now as we go to 0, I'm multiplying them by bigger and bigger numbers, root n. So the root n dn's are, in some sense, stable. I'm blowing up the smaller differences by a certain amount so that they're effectively stable. So that at any point in time, if I looked at the distribution, it would be the same size. And remember, we saw some of these examples of these, when I looked at root n x bar in the very first lab. We looked at what does convergence and distribution look like. And we had all of these things, and at the end, you had a very nice looking normal distribution, even nicer than what I drew there. But in fact, at any point in time, right, you're going to sort of be in a certain limit of the truth of 0 here. And so that's what, so this is essentially what's going on. Convergence and probability, if you remember, the picture was different. You had everything going like this. Everything was in here. And you'd end up right at 0. And there was a degenerate distribution at 0. Why this is important, now let's unpack this statement. Let's unpack this statement, okay, and see what this says. This says on a statistical scale now, because now we're talking about on a statistical scale. And I think about this as standard errors or root information scale. You can just write down the definition. The probability that a standard normal will be less than epsilon is 1 minus 2 times phi to the area to the left of epsilon. And now I can move my sigma square root n's over here. So this says the probability that x bar minus mu is within epsilon standard errors. This is epsilon standard errors. Is some fixed probability what it is, epsilon. So the probability that you're within 1.96 standard errors is 95%, right? Probability within 1.96 standard errors is 95%. That's kind of what this says, right? So here you're measuring how far away are you on standard error scale. And it doesn't matter how large you get, your sample size gets, because you're always going to have a sampling distribution. And if you measure divergence from the truth in terms of units of the standard of the sampling distribution, standard errors, that is constant. right? Because standard errors have a root n in them. So you've eliminated the difference. You've eliminated this shrinking piece. And what this says is that there is some positive probability that the difference between the sample mean and the true means will be less than epsilon standard errors. Okay? Now, this happens because the benchmark for different shrinks with the estimated differences. So notice that while this thing, the differences shrink to 0, this thing gathers around 0, and that was just the picture I was drawing above. So basically, the chance of being within epsilon units of the truth will go to 1. And you just got to take a large enough sample size, and your sample mean can always be within epsilon units, original data scaled units, meters, whatever it is, of the truth. But if you want to be within epsilon standard errors of the truth, then you can never achieve that with 100% probability. And part of the reason is that because epsilon standard errors changes, its definition is changing as the sample size agrees. Its scale is changing. Here's another way to think about it. And as I was thinking, here's x bar, right? Here's x bar n. And let's draw our regular picture. And so we have things converging here. We have things converging, right? And so the very first thing that we talked about was like this. Here's epsilon, here's minus epsilon. Eventually, there's some point n at which all of the sample paths are within epsilon of the truth. Truth here is mu. Okay? You just may have to wait. For some cases, n may be 10. For some cases, it may be 100. That's the first part. That's this top part right here. That's this result here. Okay? Now, this result says something different. This result says, hey, what's the chance that you're within epsilon standard errors of the truth? Well, these look very different. So epsilon standard errors, and I'm going to exaggerate here, look like this, if you can see. Now these are parabolic, or they look like they're root n here. And so what happens is these get very close. So even out here, you can miss in the tails. And you're going to miss basically 1 minus z, 1 minus epsilon times 2% of the time. And that's because what you're saying is, I don't just want to be close to mu in terms of absolute scale. I want to be with epsilon standard errors. And why this is important is because when we do statistical hypothesis testing or confidence intervals, we're going to measure how far off we are in terms of standard errors. It's a relative measure. It's a statistical way of measuring how far you are. In terms of science, you can way long be almost exactly at where you're at, because the clinical difference may have been established a long time ago. And this is why we say that clinical significance and statistical significance are not the same thing. All right, here's just another graph. This is in the code. I'm going to talk about the code in class, but here's just a graph to show you in terms of a likelihood function. Again, here's another way to think about what's going on. So I have 3 likelihood functions here. And the blue has 1 observation, the red has 10, and the green has 100. And the truth is 0. And you can see as the data gets bigger, the likelihood function is converging to the truth. And of course, this is on the actual scale. So this is the first example. Okay? So here we have x bar converging to mu in probability, basically. That's what we're looking at here. And as n gets big, the likelihoods get skinnier and skinnier and get skinnier as n gets big. All right. Now, what happens if I change the scale? So for each one of these curves, I'm going to draw the curves, okay, on top of an axis where the axis is scaled by 1 over the square root of n. So for one of them, it'll be scaled 1 over square root of 1. One of them will be 1 over square root of 10, and one will be scaled by 1 over the square root of 100. This means I take this number and I multiply it by the entire vector here to expand that axis, to stretch it out. And when I do that, I get this picture down here. And I've drawn the scale for you. So here's the absolute scale. This is the absolute scale. And this is basically the absolute scale. So this 4 and that 4 is the same. This 1.26 and this 1.26 is the same. And this 0.04 is basically the same as this 0.4. So effectively what I've done is for each likelihood, I've taken their x scale and I've stretched it out. I've pulled it apart and then aligned these up so that you are all the 2 standard errors. This is the column with 2 standard errors. This is the column of 4 standard errors. So that everything's aligned on the standard error scale. And now what do you see? What do you see? Well, okay, all of these things, they all have the same width. And they have the same width because I made them have the same width. And we're going to do most of our statistical work, properties, by looking at distributions of estimators and how they behave. And we're going to talk about things on the square root scale, on basically, the standard error scale, not the absolute scale. So we're always going to have to keep in mind that just because things are different statistically, or there's not perfect behavior statistically, doesn't mean that scientifically the data really are establishing what we want. And that's why things like confidence intervals, I think, are very useful, because they're always on the original absolute scale and on the original measurement scale. And you can assess measurement error and how far you are from the truth and things like this on the original scientific scale, rather than living in stat world where everything is in how many standard errors are you away from one thing from another. Okay, this is a good, this has been a good discussion. Or even better, this has been good me talking for too long. And if you have questions about this, let me know. Discuss it with the TAs. This is important to get a handle of. All right. Thank you.